Hello, this is video on chapter 7. I hope you're doing well. So let us get started on chapter 7. All right. So I'm going to do it by this PowerPoint that includes all the sections in chapter 7. So we are going to talk about systems of linear equations and systems of nonlinear equations and the use of matrices to solve them. So let's get started. So you have heard of equations, solving equations. So if you want to solve equations, you can, for example, if I ask you there is a number, if you multiply it by 2 and then add, let's say add 1, you get 5. Then obviously you know that this is a linear equation and you can easily solve it. So you get the 2x by itself on one side, so x equals to 2. So that's easy. But what if you're given two equations? So you're given two equations. Let me pick a white one so I can write on this. So we got this equation and we got this equation. What does that mean? That means it's like I'm giving you, the question is, I'm asking you, there are two numbers. If you add the two numbers, you get 15. And if you subtract them, you get 10. What are those two numbers? Now you might say, well, is 10 and 5. Well, it's true, 10 plus 5 is 15, but what about 10 minus 5? 10 minus 5 is not 10. 10 plus 5 is 15, but 10 minus 5 is not 10. So it doesn't work. So to solve this, what we do, we use some kind of method we have to use to get these equations to have only one variable, because with two variables we can't solve them. So one way to solve this, of course, is to somehow get rid of the variables, one of the variables. So how do you get rid of one of the variables? We can do two methods, substitution or elimination method. So we're going to go through all of that. So to find x and y, we're going to solve these equations at the same time. So it's not enough to find two numbers that satisfies the first equation. We have to find two numbers that satisfy both, first one and the second equation. Okay? So this structure is called a system of linear equations. It's a system of linear equations. Now, a linear equation is basically an equation that has all the variables are to the first power, right? You see that? So it has a structure like this. There's some coefficients like a1, a2, a3, all the way to whatever number you have, and whatever number of variables we have. And then the variable number 1, number 2, number 3, and so forth. Now, you can name them differently. You can call this x, call this y, call that something else. But if you name them with subscript, that there is no limit to how many variables you can have, right? If you call them x, y, z, then you have like 26 letters, and then after that, you run out of letters, right? So this is a linear equation with n variables, right? Now, if you couple a bunch of linear equations in one system together and solve them at the same time, you get a system of linear equations. For example, this one is a 2 by 2 system. What does that mean? It means two equations and two variables. So this has two equations, has two variables, right? And this system right here has two equations, but it has how many? 3 variables. So this is a 2 by 3 system. This system has 3 equations and 3 variables. So it's a 3 by 3 system of linear equations, right? Okay, so how do we solve these? Well, the best way to solve this kind of system is by the method of elimination. Elimination method means basically to find x by eliminating y, or to find y by eliminating x, right? So how do we do that? Well, we have to think about adding the equations. So if this is equation number 1 and this is equation number 2, then we think about how can we get one variable eliminated. Well, we can do this. We can multiply the first equation by 2, right? Why? Because if you want to get x eliminated, then if you make this 4x and negative 4x cancel. So we're going to add equation number 1 and equation number 2, right? Now, to add equation number 1 and 2, what do we mean by that? So we're going to add equation number 2 to equation number 1 times what? Times 2. So let's see. So 2 times the equation number 1 would be 2 times this, right? So it would be 4x plus 6y equals to 8. And then equation number 2 is negative 4x minus y equals to 5. And then what do we mean by adding them? We mean adding the left sides and adding the right sides. So that would be 0, that would be plus 5y, right? Equals to what? 13. So that is now the equation that we can solve because it has only one variable. So that equation, y equals to 13 over 5. And now we're going to take this and substitute it back into one of the equations to get x. So we can choose the equation number 1. So in equation number 1, 2x plus 3y, and y is 13 over 5, equals to 4. Now from here we can isolate x, and you know how to do that, right? So multiply and you get 39 by 5, and then move it to the other side, subtract it from 4. So 2x is negative 19 over 4, because 4 with the denominator of 5 is what? Is 20 over 5. So 20 over 5 minus 39 over 5 is what? Is negative 19 over 5. And x is negative 19 over 10. So that's the solution. And notice that the solution is given as an ordered pair, right? That's the solution. Okay, so this is called the method of elimination. We could have, multiplied the bottom one by 3 and then add it to the top one to get rid of y. We could have done that. We would have gotten the same answer. All right, so solve the system by graphing. We can also solve the system by graphing the system. How does that work? Well, in order to graph this, we know this is a line and this is a line. So to graph it, we have to solve for y, right? We have to solve for y. This way we can graph it with a calculator or by hand. We could graph it with a calculator. So let me use a calculator to graph it. There you go. So to graph it by the calculator, first you have to convert these to mx plus b form, right? So move the 2x to this side and divide everything by 3. That's what you get, right? You don't have to simplify it. You could just write 3y equals to 4 minus 2x. So y equals to 4 minus 2x divided by 3, right? And that's what this is. You don't have to simplify it. You can just put that in the calculator. You see 2. So you can just put parentheses 4 minus 2x divided by 3. So that's one equation. And the other equation, you just move the y to this side. You just move the y to this side and move the 5 to the other side, right? Move this to this side, move this to this side. So y equals to negative 4x minus 5, right? So we get negative 4x minus 5. That's the second one. Then you go to zoom 4 or zoom 6. That's the first one. Here's the second one. So what we need is that intersection right there. Intersection of the two is the solution. So let's go to second. See the second here? We go to second, and then we go to calculate, which is right there. So second, calculate, and then we pick number 5, which is intersection. So number 5. Now it picks one of the graphs for you automatically. It says first curve is already picked. Then press enter. And the second curve is already picked for you. So if you can scroll and see where the point is. Right now the point is to the right, we know. So the point right now is at x equals to 0.4, which is down there. So we need to bring it back. So let me go to zoom 6 so we have more room, and then we're going to redo this because we want to have more room. So I went to zoom 6. So we go to second, calculate, number 5, and you see where it is right now, the cursor right there. So we want to press enter and then enter again because the cursor is right there. See it? Is on the second line, so that's good. Press enter, and it says guess. Just go closer to the intersection and press enter. So negative 1.9 and 2.6 are the solution. They're the solution for this system. Okay, those are the solution for this system. So that's how we do it, by graphing. We can actually graph. All right. Now here we can add. Here's another system. It says add the equations, and we can get rid of what? Get rid of y, right? And then, so this equation plus this equation is going to be x plus y plus x minus y. The y's go away, so we get 2x. Then 15 over plus 10 is 25. So x equals to 12.5. Then we take 12.5 and substitute in one of these equations, doesn't matter which one. So let's pick the first one. So 12.5 plus y is 15, so y is 2.5. So the solution is 12.5, 2.5, right? So it looks like the method that we are using to solve systems of equations has to do with modifying the equations by multiplying by a number and adding it to another equation, right? Or just by multiplying an equation by a number, or by adding the equations. We can also switch the places if it's necessary. That doesn't change anything, right? All right. So here, using graphs of these, so you can graph this by hand. If x is 0, y is 15. So we get a point right there, right? And if x, so that's the point right there, and if y is equal to 0, then x is 15, so we get this point. So then we can graph this blue one, and then the red one, x equal to 0, y is negative 10, so it's going to be here, and when y is 0, x is 10, which is over here. And then we graph the red one. The point of intersection right there is the solution, and as you see, that's 12.5, and that's 2.5 right there, and that's the solution that we have. So the systems of equations have some of them have one solution, and some of them have no solution, and some have many solutions. So one, none, and many. Those are the possibilities, and we're going to look at an example of each. So this one is a type of system that has one solution, right? So here's another system. I modify it a little bit. So instead of x minus y is x plus y, right? So we're going to go through the same method. We are going to get rid of, let's say, y here. We try to get rid of y. So we multiply the first one by negative 1. So let us multiply this one by negative 1 and add it to this one. So multiply the first one by negative 1, we get this, and then we're going to add it to what? Add it to the second one. How? Add the left sides, add the right sides. So we get, basically everything gets cancelled here, so we get 0 equals to what? Negative 5. Now that result, right, that result tells us that this system doesn't have solution. That means regardless of what you substitute for x and y, you end up with what? You end up with something that doesn't make sense. This is false. 0 is not equal to negative 5, right? So if you combine these two equations, you get something false. That means they cannot be true at the same time. So if you pick, let's say, a number that works here, 10 and 5 here, right? 10 plus 5 is 15, but then it doesn't work here. So there is no way you can find two numbers that satisfy both at the same time. It's not possible. So we say that this system has no solution, right? All right, and if a system doesn't have a solution, then we represent the solution as empty set or just phi, which means the same thing, phi, and or we just, in English, we just write no solution, okay? Okay, now here is graphing the same system. When we graph it, what happens? You see what happens. The two lines are parallel and they have no intersection. So that means there is no solution, right? So geometrically, that's what it looks like. No solution. All right, so here's another one. I modified it a little bit. So now we're going to do the same thing. Try to get rid of y. So multiply the top one by negative 2 and add it to the bottom one. So multiply the top one by negative 2. So negative 2x minus 2y equals to negative 30. And add it to the bottom one. So that looks like everything cancels here. So we just get 0. And everything cancels here. We get 0. Whenever in the process we get 0 equals to 0 and is always true, it means that whatever that works here, for sure will work here too. No matter what numbers you pick. If they work here, it will work here too. That these two equations are actually the same. And the solution would be many solutions. Now, what are those solutions? Well, those are solutions that work for either of the equations. So we're going to write it like this. So we're going to write solutions are ordered pairs such that this little segment in math is used to put conditions after this. So we have any ordered pair except there's a condition on x and y. What's the condition? That x plus y has to be 15, right? So that's how we write it. X plus y has to be 15. Sometimes we write the conditions this way. We say, okay, let x be whatever. So if we let x be free, then y is going to be 15 minus x. So sometimes we write the solutions like this. We say, let x be free, and then y would be 15 minus x. And sometimes we all even write it vertically like that. Let x be, let the first variable x be free, and then y has to be 15 minus x, right? So your choice. And so you could also make y be free, right? So you can write it as y be free, right? If y is free, then x is 15 minus y, right? Now, because you can choose any variable, sometimes we use just a third variable or parameter, t. So let t be any real number, then the first variable is t, the second one would be 15 minus t, right? Like that, you can write it like this. All right, so those are solutions for this system here. Infinite number of solutions. They all look like that, right? So you see, x and 15 minus x. So you come up with a number for x, let's say 3. Then 15 minus 3 is 12. Let's say you say negative 3. If x is negative 3, this has to be 18. 15 minus negative 3 is 18, right? That's how we find solutions. So this expression here that I put produces the solutions. Now, graphically, what's going on? Well, graphically, if you graph this, you get this line. If you graph this, you get the same line. So that means these two lines are basically, we call that coincide. Coincide means taking the same place in space. So these two lines coincide. That means basically they share all the points. They're basically the same, right? So that means they have how many point of intersections? Infinite, right? Every point on this line is a solution for this system. So again, the systems of equations linear equations, can have one solution or none or many, right? Depending on the structure of the system. All right, so here are the 3 examples that I just talked about. 3 different examples with different solutions. First one has 1, this one has none, this one has many, right? And the geometric interpretation of that. All right. And the way we represent the solutions, right? All right. So what about a 3 by 3? Well, no matter what system we have, there are things that we can do to the equations without changing the solution. For example, we can interchange the position of any 2 equations. Let's say we are given this 3 by 3, right? Now, can I interchange the second and a third without changing the solution of the system? Yes. So we can move this over here and move this over there. We get a new system. They look different, but the solutions are exactly the same. So that's something we can do, right? So there are some moves that don't change the solutions of the systems. And those are important because we're going to use them to, in addition to matrices, to solve any system of linear equations. All right, so interchanging 2 equations is okay. Now, what about replacing an equation with a non-zero multiple of itself? So what about if we take, for example, the first one and multiply it by 2 and leave it there? Does that change the system? No. You see, suppose we have x minus 1 equals to 3. What's the solution for this system? For this equation? Well, solution is 4, right? So solution is 4. Now, what if I multiply both sides by 2? Does that change the solution? No. Because if you try to solve for x, you have to isolate x minus 1 equals to 6 over 2, which is 3. So x equals to 4. You get the same solution. So multiplying both sides of an equation by a number doesn't change the solution of it. And if it's in a system, it doesn't change the solution of the system. So we can exchange two equations, or we can multiply one of them by a number. We could also replace an equation with itself plus a non-zero multiple of another equation. What does that mean? That means you can, for example, multiply the first equation by 2 and add it to the third equation. So if I multiply this by 2, I get what? I get 2x plus 2y minus 4z equals to 4. Then I'm going to add this to this equation. So 2x plus x is 3x, 2y plus y is 3y, 4z negative plus negative z is negative 5z, and 4 plus 1 is 5, right? Now, these systems look very different, kind of, right? But what is the same? Solutions. All right. And you know why we would want to do that, right? Because remember, if we want to eliminate variables, we need to make the variables opposites, and that requires us to multiply by a number, right? Well, that is allowed because it doesn't change the solution of the system. All right, so let's try to solve a system that is 3 by 3. So here we're looking for three numbers. If you add them, you get 4. If you subtract the first two and add the third one, you get 2. If you add the first two, subtract the third one, you get 0. So to do this, we're going to turn the system that is 3 by 3 into a 2 by 2 system. So the way we solve systems of equations, no matter how big they are, right, they can have many equations, many unknowns. What we do, we keep reducing it by one variable, right? Let's say we start with 5 variables and 5 equations. We get a system that is 4 equations, 4 unknowns. We reduce it, and then by 3 by 3, and then 2 by 2, and then of course one equation with one variable, solve it. So we solve for that and we go backwards, solve for the second one, solve for the third one, solve for the fourth one, solve for the fifth one. So we reduce it to one variable, solve for that one, and go back substitute to get all the variables. That's the way we solve systems. So here we're going to pick a variable we want to get rid of, and let's pick y here. So if I want to get rid of y, I can add equation number 1 and 2. They're already ready to be added, right? Because the y's are what? The y's are opposites already. So we are going to add equation number 1 and equation number 2. So if you add them, x plus y plus z equals to 4, and add it to x minus y plus z equals to 2. What do we get? Well, x plus x is 2x. These two cancel. Z plus z is 2z. 4 plus 2 is 6, right? So that's that. Now we need another equation that has x and z in it. So what we can do is we can pick another pair, different pair. It could be this one and another equation, or it could be this one with another equation. So we take a different pair, let's say 2 and 3, right? So we take 2 and 3 and add them. So equation 2 is x minus y plus z equals to 2, and 3 is x plus y minus z equals to 0. Now notice that we didn't have to modify them because they were already what? They were already opposites. So x plus x is 2x, and in this case the y and the z cancel, and 2 plus 0 is 2. So we got lucky in this case. The z got canceled too, so it's much easier to solve this 2 by 2 system, because the second equation is kind of already solved, because x is what? X is 1. So we find x and z. So if x is 1, we can substitute back in here, equation number 4, and find z, which is 2. So x is 1, z is 2. Now we take these two to one of these equations, whichever is easier to work with, like the first one. So we're going to substitute x equal to 1 here, and z equals to 2 here. See what y is. So 1 plus y plus z equals to 4. So y equals to 1, right? What does that mean? It means that the solution is 1, 1, 2, right? 1, 1, 2. All right, now what is the geometric interpretation of a 3 by 3 system? Well, geometric interpretation would be, let me get rid of that. So what I'm going to do, I'm going to graph this in 3D so you can see the geometric interpretation. I'm also going to get rid of that plane. So this coordinate system actually has 3 axes. The red one is x, the green one is y, and the blue one is z. So when we graph an equation that has 3 variables, like x plus y plus z equals to 4, what we get is, you see the plane right there? So it's a flat plane in 3D. So basically that flat plane connects all the points in space that satisfy this equation. Now in 3D, let me turn this around this way maybe, and turn this off for a second so I can graph in here. Here we go. So let me just quickly tell you what this is about. You're going to learn this in Calculus 3, or you can just learn it yourself by yourself. So let's say, for example, if you have a point, these are called ordered triple. So let's say I have an ordered triple, 3 numbers that have to be in that order. So this is x, this is y, this is z. So the way it works is you go on the x direction 1 unit, so you get right there. In the y direction you go 2 units, 1, 2, and then you draw parallel to x and you draw parallel to y here, so they intersect here, right? Now on z we have to go to 3. So from here, if you draw up parallel to z-axis, that point is actually in a space and is a point that has coordinates 1, 2, and 3. So when we graph this, we are connecting all of those points in space such that the x-coordinate plus the y-coordinate plus the z-coordinate is what? Is 4. Now this point does not belong to that. The sum is what? Is 6. But if I did 1, 2, and 2, that's 5. That's not going to work. What about 1, 1, and 2? Yes, that one will be on this plane. So the shape that you see here, this right here as actually what? Connection of all the points that satisfy that equation. Now, the second equation gives you another plane. So x minus y plus z equals to 2. There is another plane right there. See that? They intersect at that line right there. See that line? Okay, and the is x plus y minus z equals 0. And that is another plane. Now these planes intersect. Notice that all three of them intersect at that point. And that point is a solution of that 3 by 3, which was what? 1, 2. So notice that that point in the direction of x1, in the direction of 1. And from here, if you go up 3, you get to that point. And that point in space is actually 1, 1, 2, which is the solution for this. So there could be infinite number of solutions, one solution or none. So if the three planes are parallel, you get no solution. If two of the planes are parallel and cuts through them, right, you don't get any solutions. But if the three planes are at a line, then we get infinite. All right, so I just want a geometric interpretation of a 3 by 3 system. That's what it is. All right, so let us continue with this. And that is the picture I was just showing you, right? All right. Now I'm going to talk about matrices, because matrices are used to solve systems of equations. So let's talk about matrices. A capital letter is generally used to name a matrix, like A, capital B. And the elements in the matrix, or the entries of the matrix, are named with the same letter but the lowercase. And there is a notation for it. So a matrix is actually a multidimensional number that has rows and columns, right? So to name the elements of the matrix, we use this double subscripts here, which means, for example, A11 means A is the element in the row 1 and column 1, right? And in general, we represent a matrix by collection, basically, of these elements, right? These entries. A, I, J. I is the row number and J is the column number. All right? So, for example, this is what? This is a 2 by 2 matrix. Usually we put it here, 2 by 2. And this is in order. The first one is number of rows. The second one is number of columns. So in this case, this 1 here is A11, is the entry in the row 1 and column 1. This 0 is in A22, row 2, column 2. Number 5 here is row 2, column 1. So we call it A sub 2, 1. That's 5. Okay? And so forth. So two matrices are equal if they have the same dimensions. So two matrices to be equal, they have to have the same dimensions. Dimensions refer to what? Number of rows and number of columns. So two matrices have to have the same dimensions in order to be equal. And also they have to have the same corresponding entry. So this right here is A11 and this right here is B11. Because of that 1, 1 subscripts, there are corresponding entries, right? So notice that in these two matrices, the corresponding entries are the same. So for two matrices to be the same, the corresponding entries have to be the same. All right. So how do we add or subtract two matrices? Well, to add two matrices, first of all, they have to have the same dimension, right? Dimensions. Now, all we have to do to add two matrices is to add the corresponding what? Entries. So to add these two, just add -6 to 2, 7 to -4, 2 to -8, 1/4 to -4. And we get that. So this matrix, you could call it C. C is the sum of A and B. We could also subtract them. So if it's subtraction, just subtract the corresponding matrices. Okay, so it's very easy to add and subtract matrices. They have to have the same dimensions, otherwise we can't add or subtract them. All right, so here is an example. Let's look at it. So can we add them? Yes, because the dimension of this is 3 by 2. This is also 3 by 2. So we just take the corresponding entries and add them, right? So we get that. Very easy to add matrices. What about subtracting matrices? So we can also subtract them, of course, we talked about it. Now here it says, find the values of the variables for which this statement is true, if possible. Well, if this matrix equals to this matrix, then the corresponding entries have to be equal. So that means A has to be -3, B has to be 9, -5 has to be C, or C has to be -5, and 0 has to be D, right? That's it. Based on this idea that we know corresponding entries have to be equal for two matrices to be equal, right? That's all there is to it. All right, find the product. Now, we can multiply a real number, one-dimensional number, by a matrix. How? It's very easy. Just multiply every entry by that number. So this is called a scalar multiplication. A number by itself is called a scalar. -3 times this matrix is -3 times 2, -3 times -5, -3 times -4, -3 times 0. And that's it. It's very easy to multiply by a number. Now, we want to talk about matrix multiplication. And you may think that to multiply matrices, we have to do the same thing that we did with addition. Like, for example, if we have a matrix like this, then to multiply them, just multiply the entries. Well, there is a multiplication like that, but we're not going to use it here. It's called that, Hadamard product, in mathematics. But in what we do in college algebra and the usage of matrices that we have here and many other branches of mathematics, this is not used. So how do we multiply two matrices? Well, we're going to see that. It's very easy to multiply. It's kind of vague at first, but it's not really that hard. So if we call the matrix A by its entries and matrix B by its entries, so this is matrix A is a collection of a bunch of entries and is M by N, and then B is a collection of a bunch of entries with this dimensions of n times r. So the way we define multiplication of matrices, if this one is m times n, this one has to be n times whatever, doesn't matter. These two numbers have to be the same for us to be able to multiply them. Because the way we multiply matrices is by multiplying a row by a column. So if I multiply this row by that column, then the number of entries in this row, let's say there are 5 of them here, has to be the same as the number of entries in this row, in this column. So number of entries in this row are actually number of columns, right? And number of entries in this column is actually number of rows, right? So that's why number of columns of the first one should be the same as the number of rows of the second one. Otherwise, we're not going to be able to multiply them the way that we define it. Now, you might ask, how do we multiply a row by a column? And I'm going to answer that in a second. But that's how it works. So let's multiply that. So this is so we want to multiply A times B. A is this matrix and B is this matrix. Now, first of all, can we multiply them? Let's see. The dimensions of that is 2 by 3, right? And the dimensions of the second one is 3 by 3, 3 by 4, right? That's 4 columns and 3 rows. Now notice that these two numbers are the same, so yes, we can multiply these. So the way it works is this. We take this row and multiply it by this column this way. So this is row 1, the first matrix, times the column 1 of the second matrix. So the answer to this matrix multiplication, the answer to this would be 2 by 4. So the answer would be 2 by 4. That means it would have 2 rows and 4 columns. That's the answer. Now, let's call this C, right? Matrix C. Matrix, we can call it C because we already use C. Let's call it D, right? So this would be D11. So in order to get this entry, D11, we have to do what? So D11 is the product of the row of the first matrix times the column of the second matrix, right? So row 1 of the first matrix and the column 1 of the second matrix. How do we multiply? This way. Multiply the corresponding entries like that. So 2 times 3, 0 times 4, -1 times 5, and then we add them. We get 1. So that entry right here has to be 1, which is right, we see it right there, right? So that entry is 1. And then we get the second one. This is what? This is D row 1 and column 2, right? So we can get it like that. We can get it by what? By taking row 1 from the first matrix and multiply it by column 2 of the second matrix. The same way, 2 times 1, 0 times 8, -1 times 0, and add them. All right, so that's the idea. That's how we do it. And the next one, again, 6, is what? Is D13. Is the entry in the first row and third column. So we take the first row of the first matrix and the third column of the second matrix and multiply them. Again, this by that, this by that, this by that, and add them. Okay, so if you do that, you can even do it in your head, like 2 times 1 plus 0 times 8 times 0, -1 times 0. And that's 2. So we're going to go through every element and do it like that, and then we end up with this answer right here. So the A plus A times B is done like this. So these are the other elements, right? We're going to get all of them like that, and then we end up with the answer, right? So that's the answer. We took this row right here. We took this row and multiplied by this column to get this number. Then we take the same row and multiplied it by this column to get this number. And we took the same row, multiplied it by this column to get this number. And we took the same row, multiplied by this column to get this number, and so forth. We took the second row, multiplied by the first column to get this one, and so forth. Okay, so that's the multiplication, that's how it works, and you're going to see that this is pretty useful. You see, for example, if you, let's say you're managing an apartment complex, and let's say this matrix is maybe south location, north location, and east location, and each location has 1-bedroom apartments, 2-bedroom apartments, and 3-bedroom apartments. And let's say it has this many in each location. Let's just put some numbers here, right? So that means that location south has 10 1-bedroom, 22 bedrooms, and 33 bedrooms, and so forth, right? North has 31 bedroom, 42 bedrooms. And let's call this matrix here occupancy matrix. Let's say these are the number of apartments that are occupied, right? And now we're going to create another matrix. We're going to call this rent matrix. Notice that this is 3 by 3 and this is 3 by 1. So the answer would be what? Would be 3 by 1. And we can multiply because these two numbers are the same. So let's put here 700, 900, and 1000, right? These are like prices for 1-bedroom, 2 bedrooms, and 3-bedroom apartments. So what happens if you take this row and multiply it by this column? 10 times that, 20 times that, 30 times that. So 10 times 700 is going to be 7,000. 20 times 900 is going to be 18,000, right? And 30 times 1,000 is just 30,000. So if we add them, what do we get? We get 55,000, and this would be this entry here. And then if you multiply this by the same column, you get another number. Multiply this by this, you get another number. So these numbers are what? How much rent the company is collecting from the south. This number is how much from the north, and this number is how much from the east. So this kind of multiplication is pretty useful, okay? And we're going to see how we can solve systems using this multiplication. All right, now with matrices, we also have to talk about something called identity matrix. What is that? Well, identity matrix is like 1 in arithmetic. 1 times any number is what? The number itself. Now, can we have a matrix that you can multiply by another matrix and doesn't change it? So you're going to get the same answer. So you want a matrix that if I multiply by this, I get the same answer. Now, this is only defined for square matrices. So this identity matrix that is called identity matrix is only defined for square matrices in this course, okay? So we have, this is identity matrix. So this is called the main diagonal, and this is the other diagonal. This is the main one. So you have all ones on the main diagonal and all zeros everywhere else. So here you see a 2 by 2i, and you see a 3 by 3i, 4 by 4i, right? As you see, we got what? We got on the main diagonal, they're all 1, and everywhere else is 0, right? And also 1 by 1, of course, is just number 1, right? So what do we get if we multiply? Let's say if we multiply this by that, what do we get? 1 times 1 is 1, 0 times 3 is 0, 1 plus 0 is 1. If you multiply this by the second row, second column, 1 times 2 is 2, 0 times 4, you get 2. 0 times 1, 1 times 3 is 3. 0 times 2, 1 times 4 is 4. So you see you get the matrix back. So this is an identity element in matrix multiplication. Now, since it's a square, it also works if you put it on the right side. If you multiply it this way, right? 1, 2, 3, 4. What do you get? Well, 1 times 1 is 1. 2 times 0 is what? 0, so that's 1. 1 times 0 is 0. 2 times 1 is 2. 3 times 1 is 3. 4 times 0 is 0. And then 3 times 0 is 0. 4 times 1 is 4. So you get the same thing. So I times A equals to A times I, right? Equals to A in general. Now, of course, this I is a square matrix, right? Here, my matrix was 2 by 2. But if my matrix is not 2 by 2, right? Let's say this one is not 2 by 2, is 2 by 3. So if I want to get the same matrix, right? Now this is what? This is 2 by 3. So I can multiply it by what? By a 2 by 2 I, right? On the what? On the left. And you get the same thing. But if I want to do it on the right, remember this is 2 by 3, right? So the I that works has to be what? 3 by 3 to get the same matrix back, right? So this has to be 3 by 3. You're going to have 0 everywhere else, right? So that's the idea of I and identity element in matrices. Okay, so it says find AB. Well, again, just practice this times that, this times that, right? So the first row times the first column, first row times the second column, second row times the first column, second row times the second column, and you get these. Again, this is a 2 by 3. This is a 3 by 2. So these two numbers are the same. We can multiply, and the answer is 2 by 2. All right. So I'm going to let you do this yourself, look at it, and I'm going to wait for a few seconds on this so you can stop and look at this and make sure it makes sense. C squared means C times C, and 5 times C, and then 10 times I squared, I2. I2 is just I2 by 2, right? So you see how it works here. C squared means you multiply this by itself right here, and then negative 5 times C means negative 5 times this, and then plus 10 times I2, 10 times I2, and is that. Now since these are all 2 by 2s, when you get the answer for that too, we can add them and we get that, right? All right, we'll just practice with that. Here is another example, and I'll let you look at. So here M is a 4 by 4 matrix. It says expand this. So to expand it, we have to multiply M by M, right? Then M by that, and then this by that, and this by that. So here all of these are allowed. So what do we get? We have to multiply this thing by M, and then this thing by that, and then expand it as you see, right? Now here, I times M would be just M. Here, M times I would be just M, and here, I basically times I is itself, is I4, right? And 3 times 2 is 6, so you get this. All right, so I'll let you, we're going to stop the video and see if it makes sense to you. All right, using matrices to solve linear systems. We just needed to know enough so we can solve linear systems, okay? So matrices allow us to solve systems of linear equations. And to that end, consider this system right here, right? So what we do, we take a system of equations and turn it into what? A matrix equation. So this is a matrix equation. How does this work? Well, notice that if I multiply this by this, 1 times x is 1x plus 1 times y is 1y, so it's x plus y, right? So it looks like I get this. And if I multiply this by this, I get 1 times x minus y, which is that. And then I have set this equal to what? 15 and 10, the right hand side. So if you multiply these two, you get a matrix. So this is a 2 by 2 and this is a 2 by 1. So the answer would be 2 by 1. And 2's are the same, so we can multiply. So we get a matrix that is 2 by 1, has two entries. The first entry would be, right, would be 1 times x plus 1 times y. And the second would be 1 times x minus y. And then this has to equal to 15 and 10. And remember we talked about a 2 by 1 matrix and a 2 by 1 matrix have to be equal. Now remember, x plus y, that doesn't mean it has two columns. It has only one column. The entry is x plus y. Okay? So this entry has to equal to that, and this entry has to equal to that for this matrices to be equal. Well, what do we get if we write that down? We are going to get the system back, right? So that means this matrix equation is equivalent to what? To that system of equations. So we convert it to a matrix equation, and now we can solve this system easily using matrix operations. How? Well, here's the idea. So that means if you have a system, you can convert it to this, and if you have this, you can convert it to a system, right? Now, basically, these numbers are the coefficients of the x and y in each equation, and the numbers on the right-hand side are just the numbers after the equal sign, right? So the wishful thinking here is that if we could get rid of the variables, it would be nice, and it's possible to do that. So we're not going to get the variables involved, and we're not going to write it as a multiplication. We're going to write it as a matrix that is called augmented matrix. Augmented means something added to it. So we're going to take the coefficients of x, y, and the number on the right hand side and put them here in a row. And then coefficients of the second equation, 1, -1, and 10, and we'll put them here. Right? Now, sometimes they put a little line here to separate the numbers from these, but you don't have to do that. Just leave it like it is. This is good. So this is called the augmented matrix. So if somebody gives you this augmented matrix, you should be able to write the system, or if you're given the system, you should be able to write the augmented matrix. It's very easy, right? Now, think about it. If we had an augmented matrix that looked like that, then this system would be solved. Why? Because think about what this means. Well, this means what? It means 1 times x plus 0 times y equals to that, whatever that is, a number. 0 times x plus 1 times y equals to that number. Now, this system is already solved because x is that and y is that, right? So if we could turn that augmented matrix into this, we have solved the system. And it turns out that Remember the operations that we did with the equations, adding two equations, multiplying one equation and adding it to another one, or exchanging the equations. All of those can be done, instead of to the equation, we can do it to the rows of this matrix. So we can actually do the same thing to the rows of the matrices. So matrix of the augmented matrix can be converted to this form. You could do it by hand or calculator. So I'm going to do it by hand and calculator. Okay. So the goal is to take a system, write augmented matrix, and write it this way. And this is called the row reduced echelon form in the calculator. I'm going to show you where it is. So our goal is, if possible, to take this and turn it into what? This. This process is called converting the matrix to reduced row echelon form. We do this using row operations, which are the same procedure applied to the equations of a system in order to solve it. So what are the row operations? Interchange the position of any two rows. You can do that. You can replace a row with a non-zero multiple of itself, and you can replace a row with itself plus what? A non-zero multiple of another row. And we did that with equations. So let's see. So we're going to convert the system first to what? To augmented matrix. Then our goal is this. Now, the procedure becomes difficult and tedious if you don't do it in an organized manner. So what I want to do is I want to make this column look like this column. That means first I have to make this number 1 if it's not 1, and then I have to use it to make this 0 using operations, row operations. All right, so let's just start. So first we want to make this look like that. So the first step is done. This 1 looks like the one that we have here. So that's done. Check. Now we have to make the number below it 0, but we have to use this 1. So we're going to take this row, multiply it by what? By -1, and add it to row 2. So here is row 2, right? And the row 1, we're going to multiply it by -1, -1, -1, -15. And now we're going to add these. 1 plus -1, 0. -1 plus -1, -2. 10 plus -15, -5. So we're going to pick this. You see, we put it in row 2. So we're going to put this in row 2. We're going to leave the row 1 alone, even though we multiplied by -1. But we did that because we wanted to multiply add the result to row 2. So you don't want to change row 1. You want to leave it alone. So your row 2 would be row 2 plus -1 times row 1, which I did here. Okay, are we done? Yes, with the first column. Now we go to the second column. We're going to make this number 1. How do we do that? We divide everything by, multiply everything by 1 over -2. Remember, we could do that with equations. We could do that with rows too. So we're going to multiply this by 1 over -2. So let's do that. There. So we got the first one under control, so we are working with this. So we're going to make this positive 1. How? We're going to take row 2, which is this, divided by -2, and then add it to what? Itself. Right? So you can just think about, just replacing it, not adding it. Let me get that. I said adding it. So you're going to do this and replace put it instead of row 2. So what would that be? That would be 0, that would be 1, and that would be 5 over 2. Okay, so we're done with that. So it's just one row. You can think of dividing by -2 to make it 1. All right, are we done? No. We got this part. Now we have to make the number above it 0. So now we go to this. We say, okay, our goal is to make this 0 using this 1. So how do we use this 1 to make that 0? Well, we can take take this row and multiply it by negative and add it to this row, right? So we're going to take row 2, multiply it by negative 0, -1, -5 over 2, and add it to row 1, 1, 1, 15. So that gives us just what? So we're going to add this to row. So this gives us the same. This is just 1. This is 0. And what's 15 plus -5 over 2? We have to add them, right? So 15 plus -5 over 2. Well, 15 is 30 over 2, plus -5 over 2 would be 25 over 2, right? So that's 25 over 2. Now we're going to take this and write it for first row, right? So that's the first row. Now we accomplished what we wanted. The first column looks like that. The second column looks like that. Now, this is not magic, is math. And you see right there, these are the solutions. Remember this? We solved it before. The solution was what? 12.5 and 2.5. Now we got the solutions right here. Okay? So this process, we can do it with what? We can do it with calculator. So let me show you how to do this with the calculator. So the way we do it with the calculator is by going to matrix and go to edit. So matrix is where? Matrix is second, that matrix. And when you go there, you go to edit. You scroll right to edit. And under edit, you pick A, matrix A. Now you make the dimension of the matrix the same as the dimension of your augmented matrix. So 1, 1, 15, that's 2 by 3. So we put 2 by 3. So then we put 1, enter, 1, enter, 15, enter. So calculator, let me do this. It didn't get my entry. So we're going to make it 2 rows by 3 columns. Okay, now I got it. 1, 1, 15, and then 0, negative, -2, -5. Okay, so that's my matrix. Now calculator, you get out of it, second, quit, you get out of it. Now calculator has a feature that can actually take this matrix and give you this matrix. So that procedure is under matrices, of course. You go to second matrix and you go to mathematics in the middle. And then go down to RREF, the row reduced echelon form. Pick that one. It puts it on home screen. And then you put the matrix that we just created in there. Where is the matrix that we just created? We go to matrices. Don't go to edit. Right here, the first column, you pick A. So you press enter, or just press 1. And it goes there. And then press enter. There. Everything we just did here, all the arithmetic that we did here, calculator did in fraction of a second and gave us the answer, right? You see the answer right there? That's the same answer. See, 1, 0, 0, 1, 12.5, 2.5. There. You see, solving systems of equations is much, much easier with matrices, right? Okay, so to solve systems, again, that's what we do, right? So let's do another one. So if I want to solve this, what I'm going to do, I'm going to matrices, then create a matrix, which is augmented matrix. Now the augmented matrix for this would be what? Would be this right here. So all you have to do, make sure you organize your variables so there are what? They're in order. So you know the coefficients of each variable because they could be missing. If they're missing, we have to put 0 for the coefficient of the variable. So the first row is 3, negative 1, 1, 8. 3, negative 1, 1, 8. The second is 1, 2, negative 1, 4. 1, 2, negative 1, 4. And 2, 3, negative 4, 10. 2, 3, negative 4, 10, right? Then, what's the dimension? 3 by 4. So we put 3 by 4. And we put the numbers there. 3, negative 1, 1, 8, 1, 2, negative 1, 4, and then 2, 3, negative 4, and 10. There. So I'm going to get out of here and go back to matrix and get matrix A and put it in home screen just to make sure I correctly entered the numbers, right? And it looks like it's correct, right? 1, 2, that, 2, 3, negative. Yes, you want to do that so when you get the solution. So let's solve this now. How do we solve it? Well, here you go. We are going to go to matrix and go to math, get our RREF, and then go back to matrix, get matrix A and press enter. There. In a fraction of a second, we got the solution. So the solution, the RREF is 1, 0, 0, 0, 1, 0, 0, 0, 1, and is 3, 0, negative 1. So that means if you convert that back to XY system, what would that mean? That means 1 times X, right, plus 0 times Y plus 0 times Z equals to 3. That means X is 3. What does that mean? That means 0 times X plus 1 times Y plus 0 times Z equals to 0. So that means what? Y equals to 0. And then 0 times X plus 0 times Y plus 1 times Z equals to negative 1. That means Z is negative 1. So we just solve this system, right? Using what? Using matrices. Okay? All right. So I just talked about this, how to do this with the calculator, right? So the trick is here you don't even need to write the matrix equation. You just need what? Augmented matrix. All right. So now what happens if you have a solution? Well, if you have a solution, then you end up with what? You end up with RREF that looks like 1, 0, 0, 1 and something here and something here. Or 3 by 3 or 4 by 4, doesn't matter. But what happens if you don't have solution? Well, if you don't have solution, then you end up with a matrix that looks like this. Well, let's say, for example, the last row will look like all zeros except for the last number. It won't be 0. What does that mean? Well, it means that the second equation is 0 times x plus 0 times y equals to 1, which doesn't make sense. This is false. So if you get a row of zeros at the bottom with the number right here, non-zero, this means no solution. And what happens if you have many solutions? Well, if you have many solutions, this is what happens. You get a matrix that has one row, all zero at the bottom. You see, one row of zeros. When this happens, it means infinite number of solutions. And to write the solutions, all you have to do is what? Just use the first row. 1x plus 1y equals to 15, right? So that means you get this, and that is the solution, is infinite number of solutions. Okay, so we got that was no solution, one solution, and the solution is 2.5. And this is the second case where we get the row of zeros, right? Except for the last number, right? And then here is another one where we have a whole row of zeros, which means infinite number of solutions. Okay? All right. So here is an application. It says a family reunion. And at a family reunion, there were only blood relatives consisting of children, parents, and grandparents in attendance. Now, there were 400 people total. There were twice as many parents as grandchildren, and 50 more children than parents. How many of each? So to solve this kind of situations, we let variables equal to the three unknowns here. So x is number of children, y is number of parents, and z is number of grandparents. What do we know? We know that the sum is 400. We know that the number of parents is twice the number of grandparents, right? And we know that number of children is 50 more than parents, right? So that gives us three equations. But we're not going to put this in the calculator the way it is, because remember, in the calculator, they have to be in order. So we're going to organize it like this. So the first equation is good. The second equation is missing x, so 0x. And this z has to be on this side, so we have to move it and change its sign. The y is in good place, so it's going to look like this, the second equation, if it's organized. And the third one, x comes first, then y comes to this side, becomes minus y, and the z is missing on this side, so we put 0 times z. And 50 stays on this side. Now we write the augmented matrix, which is what? Which is this, right? And then we put in the calculator, RREF it, here are the answers. X is 190, y is 140, and z is 70. Okay? So it's a pretty easy process if you know matrices. So I'm going to do another short video for this chapter where I'm going to talk about inequalities and systems of inequalities. This video already became too long, but that's okay. We learned a lot in it. So I'm going to come back here and say bye to you, and I hope you're doing well still. I'll see you in the next video. Take care of yourself and others. Bye-bye.